Good morning, all of you. Am I audible? Am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, thank you. Just a minute for me.
So in the voltage and feedback, if you have to be see, configuration is very much clear that we have already discussed as well in the unit number 2 also. So when we have to be sample the output voltage and then feed it to the parallel to the input network. So it is called the voltage shunt. So in here, if you have to be see these two words. So the first one is voltage. It is nothing but the type of sampling, and this is the second one. It is referred to the type of mixing. So here you can see, please everyone note down this diagram. Both diagram is actually same and reflecting the just voltage shunt feedback amplifier. So if you have to be see these two diagrams, you would be found that this is the op amp and non-inverting terminal is connected to the ground. Because we are learning here about the uh, negative feedback. So you have to be see that uh, feedback is coming out from the output through the RF and it is fed to the inverting network. Okay, and here we have connected the input voltage source to the inverting terminal. And if you have to be observe, this diagram is redrawn and arrange the components in a form that we would be easily analyze this circuit. So you would be found that here now inverting terminal is at the top and non-inverting at the bottom, and it is very much clear now from the diagram that once feedback network through the RF is connected in this particular amplifier. And here we are doing the voltage sampling. So obviously this feedback network would be connected parallel to the output terminal and it is fed to the input side in shunt or in parallel. That's why it is here connected to in parallel. So it is very simple configuration. We have already discussed lots of the terms about the feedback networking. So now we have to be analyze this circuitry. Then you have to find out that as non-inverting terminal is connected to ground, so there is a voltage. You can refer it as a so it is 0. And here if you have to be see voltage is supplied in the inverting terminal through the V1 V in through the R1, and if you have to be observe the current, so the current I1 is flowing through the R1, and but when it is reached to this inverting terminal, as we know that ideally input resistance of the amplifier is infinite, so no current would be enter into the op amp. That's why IB is mentioned here as 0. So all this current I1 would be diverted to the feedback network, that is you can consider as a IF, feedback current. Okay, so I hope all of you have drawn this. So I would be move to the next slide. You would be found that you would be find that the input voltage drives the inverting terminal input voltage drives the inverting terminal, and amplified as well as the inverted output signal is applied to the inverting input via feedback resistor RF. And as we see that this arrangement would be from the negative feedback, as I have told you already. So that's why what happens, if there would be any increase in the output voltage or signal, that would be result this would increase in the output signal would be result in the feedback signal into the inverting input signal, and that would be decrease the output signal, means it would be counterbalance this increase in the output signal. So this would be your gain would be stable. And as we have seen that non-inverting terminal is already grounded and R1 is connected with the input source V in. So if you have to go for the mathematical analysis, this is the equation that I have written here. The closed loop voltage gain AS can be obtained by using the KCL, Kirchhoff's current equation, at a node V2. So if you have to refer the diagram, you would be found that there is this is your V2 and this one is V1. As it is connected to ground, so it would be always 0, and V2 is here. You can define this V2 as here KCL. I1 is equal to IF plus IB. That you can very much easily see here at this particular terminal V2. One current, incoming current is I1 and two outgoing current IB and IF. But as the input impedance of the op-amp is infinite, it is 0, IB is 0. So whole the current would be nothing but the IF is here. So if you have to be assume this way, you would be found that IS is nothing but equal to the I1. So now we have to write the equation of I1 and IF. So what is the I1? If you have to be refer here, so if you have to refer on this particular network, you would be found that I1 is what? V in minus V2 upon R1. As per the Ohm's law, V in minus V2 upon R1. At the same time, what is IF? That you can say V2 minus V0 upon RF, that we have written here. So I1 is V in minus V2 upon R1 and IF is V2 minus V0 upon RF. And also we have to know that the value of differential input voltage, that is V1 minus V2, means the voltage appeared at the inverting and non-inverting terminal. Okay, so V1 is a non-inverting terminal voltage, V2 is the inverting terminal voltage. The difference of both is nothing but your differential input, that is equal to output upon open loop gain. Generally we refer V0 is equal to A into VD. So here VD is equal to V0 upon A and VD is nothing but V1 minus V2. So as per our assumption, we know that V1 is a voltage at the non-inverting terminal and non-inverting terminal is actually grounded. So V1 is equal to 0. So we would be substitute the value of V1 in this equation. So you would be found at 0 minus V2. So V2 is equal to minus V0 upon A. So this, there is a negative value of the V2, that would be give us a message. We would be see. Can anyone say that this negative value is what? It is given us the message that it is working as an inverting amplifier. And your output signal would be actually inverted with respect to the input signal by the amount of 180 degree out of phase. Okay. So by keeping this value in your mind, you can give the equation number as well. So it would be give you the easy interpretation. So you would be got this is the equation number 3 further we would be continue it. So now this value of V2 would be substituted. One thing you can refer, just give you the unit equation number 3 is here, okay, and then it is 4. Now substitute the value of V2 into the equation number 3. You would be found that V in minus V2. So V2 is minus V0 upon A. So V in plus V0 upon A upon R1. It is equal to V2 minus V0. V2 is what? Minus V0 upon A minus V0 upon RF. Okay. So AF is what? V0 upon V in. Okay. So I have not gone into the detailed rearrangement of this equation. You can keep some space on your notebook and you can do the further analysis. 2 lines you can leave as a blank between this statement and this statement. And then finally, you would be, when you rearrange this equation, LHS and RHS, you would be found this equation of closed loop gain, that is AF is equal to V0 upon V in, that is equal to RF into A upon R1 plus RF plus AR1. And as we know that, what is A? A is basically open loop gain. AF is the closed loop gain. And we know that ideally op-amp has open loop gain is infinite. Practically it is very high for our op-amp, that is we have taken as a 741. So it is nearly 2 lakhs. So as A is very high, therefore you can consider or you can approximate actually AR1 is very much larger than R1 plus RF. That is AF is equal to, if AR1 is very much larger, you can neglect these terms in the equation number 5. So finally, you would be got A1 is equal to minus RF upon R1. It is your minus RF upon R1. Okay, and there is a one negative sign I have missed here, that would be remaining. Okay, so in this way, you can say, from the past discussion of the voltage series feedback also, so minus RF upon R1, you can also write it as minus 1 upon B. B is what? Feedback factor or feedback gain. Okay, so in this way you can say that your closed loop gain is now again independent of the op-amp parameters or networks, resistor, you can say the op-amp parameters. Okay, so it would be only depend upon feedback resistor and input resistor. So it would be make this arrangement free from the temperature change or some other environmental changes. Okay, so this is the equation of closed loop gain for the voltage shunt feedback. So please all of you have note it down, and this is the equation number 7 also you can put up here for your easiness of the understanding. And B is equal to R1 upon RF, we know that. Okay, so now we have to find out the other parameters of the voltage shunt feedback using operational amplifier. This is a very common remark from previous analysis that we have already seen, that because there is a negative sign, that's why you can say that output signal is out of phase with respect to the input signal, and it is the main reason why we have say this as an inverting amplifier with feedback. And gain is depending upon actually the feedback resistor and the R1. So you can adjust the value of the gain by adjusting the ratio or value of these two resistors. Now we have to see one more concept of the inverting input at virtual ground. So if you will refer the figure 9, means the diagram of the voltage shunt feedback that we have seen earlier, the non-inverting terminal is grounded and input is given to the inverting terminal through R1. So the difference input voltage VD is ideally 0. Why? You can refer here the diagram in the figure 9. You can see here that non-inverting terminal, that is V1, is grounded, means it is 0, and as it is 0, then according to the virtual ground concept, you have to be also assume that V2 is also equal to 0. That means VD is what? V1 minus V2 or V2 minus V1, whatever you can refer here. So it would be coming as a differential input voltage would be coming as the 0 here. Okay. So this is the because of the virtual ground concept only. Okay. Generally in the analysis of the op-amp based circuitry, we have to be use the concept of virtual ground that we would be learn in the next unit also in detail. So as the differential input voltage VD is ideally 0, that is it is a voltage that at the inverting terminal is approximately equal to that of the non-inverting terminal V1, or in other words you can say that inverting terminal voltage is approximately at the ground potential, and that is referred as a virtual ground. So physically it is not at the ground, but virtually it is at the ground potential because of the concept of virtual ground. Okay, and this is a very important concept whenever you have to be analyze any circuitry using the operational amplifier. And how it is possible you can see here, and through this using virtual ground concept you can again find out the closed loop gain equation. Okay, instead of going to the previous analysis in detail way, you can use this assumptions of the virtual ground and very easily you can find out the closed loop gain equation. So as per our assumption, V1 is at 0, so V2 is also considered as a 0, VD is equal to 0. So in that case, I in is equivalent to the IS, that is V in minus V2 upon R1 is equal to V2 minus V0 upon RF, and as V2 is 0, so V in upon R1 is equal to V minus V0 upon RF. That means V0 is equal to minus RF upon R1 V. Means it is inverting amplifier. Okay. So this is another way that you can also use for analysis of this circuitry. Now we have to be find out the first parameter. We have already calculated closed loop gain. Now we have to be come for the second parameter, that is input resistance with feedback. So to find the input resistance, Miller equivalent of the feedback resistor, RF is obtained. That is RF is splitted into two Miller components. So please all of you noted down this diagram where I have converted the regular voltage shunt inverting amplifier into the Millerized feedback resistor. So you can see here what is the difference between the figure 9 and this is that whatever the resistor feedback resistor that is connected between the input inverting terminal and output terminal, that has been splitted into the two parts. We have already learned the Miller's theorem in unit number 2 in very detail, so I do not go for the detailing of this again. But we know that whenever any network or resistive network or any other passive device network is connected between the input and output terminal of the amplifier circuitry, so to ease of the calculation and as well as the analysis, we have to be use a Miller's theorem, through which we would be split the feedback component into two separate parts, and one part is connected to the input network, another part is connected to the output network, and there is some mathematical relationship that we have to be used to refer this two splitted resistors. First one is at the input side Rf upon 1 plus A, and second one is Rf upon 1 plus 1 upon A, or you can say Rf into A upon 1 plus A is here. Okay. So these are the two Miller resistance. One is connected output network, another is connected input network. But we are actually here for obtaining the input resistance, so we would only refer this part of the circuit, input part of the circuitry only. Okay. So this is very important analysis. Please note it down this diagram. Okay. Now, after splitting of this feedback resistor into Millerized resistances, you can see here there is a two resistance we can see here. One is Rf upon 1 plus A, and another is input resistance of the op-amp, internal resistance. Ideally it is infinite, but practically we have to be taking some very high finite value, that is Ri. Means Ri is here very high as compared to the R1. Okay. So if you have to be going to analyze this input network, you would be found out that Ri parallel Rs upon 1 plus A, it is in series with respect to the R1. So when you have to be find out the equivalent resistance of these two, so you can see that this would be become a closed loop network where R1 and the equivalent of Rf upon 1 plus A and Ri would be in series. Okay. So I hope all of you have drawn this diagram. And another side of the network, I have shown the output network where we have to be dissolve this op-amp into the one voltage source that is having A, VD, and output resistance R0, and this is a load resistance RL is there. The use of this network would be in the next analysis of the output resistance. So you can see here the input resistance would be RIF with feedback. RIF is equal to R1 plus Rf upon 1 plus A in parallel with the Ri. So this parallel combination would be in series with the R1. And we know that Ri is very high value, ideally infinite, practically very high, and A is also very large, ideally infinite and practically 2 lakhs. So you can say that as Ri and A are very high, so their parallel combination would be equivalent to the 0. Okay. So if it is equivalent to the 0, then RIF is equal to only R1. Okay. So here input resistance with feedback, it is equivalent to the R1 only. This is the analysis for the input resistance of the voltage shunt feedback. Now come for the output resistance with feedback, analysis of this particular part. So for this, we do not go for the Miller approximation. We would be directly draw this diagram of the voltage shunt feedback. Only what we have shown here, it is very much similar to the figure 9, where only I have shown input resistance, internal input resistance Ri between inverting and non-inverting terminal, and come to the output network now, that is finite voltage source A, VD, then R0 in series, and one arbitrary, or you can say dummy voltage source has been connected at the output network. And for the analysis of output resistance, we always short the input voltage source. So here also we have shorted this input voltage source here. Okay. So here output resistance could be obtained by using the Thevenin's equivalent circuit. And this Thevenin's equivalent circuit only applied at the output network. Okay. Means when you have to be looking from output to the input side. So you have to be always observe to find out output resistance. You have to observe from right to left direction. Means you have to observe from here into the circuitry. So you can see here as V naught as the output voltage source that would be responsible for drawing the current I naught. And at this terminal node, you can refer this suppose node A, where this current would be divided into two parts according to KCL, IA in IB. But which current is dominant? We have to be see further. I hope all of you have drawn this circuitry. This short circuit is very much important. See here. Okay. Now, if you have to be see that according to this node A KCL, we are going to apply the KCL. So it would be I naught is equal to IA plus IB. Since output resistance R naught is very small as compared to RF plus R1 parallel RI. Okay. So when you are looking this circuitry from the right hand side to left hand side, you could find out that the current would be divided into two parts, IA and IB. IA would be flow into the R naught, okay, and IB would be flow through the RF. And if you have to be observe this end, RI is in parallel with this network R1 plus RF. So you can see here that we have written, if you have to find out this RF, this is the network RF plus this RF would become here plus with R1, and you have to bring this network if in this way parallel. So it would be R1 and RI would be looking as a parallel network. Okay. So R1 parallel RI plus RF, and it is a very large resistance because the value of RI is very large. Okay. So RI is very much larger as compared to the R naught. This equivalent is very much larger than R naught. So you can say that as the resistance is very high in this network of the IB, so IB is negligible, because if resistance is very high, the very less amount of current would be flow. And the other side, R naught is very small, so maximum current would be flow through the R naught. So in this way, IA is larger than the IB. So you can say that output current is equivalent to the IA. And then you have to apply the KVL on this output network. So it would be find that V naught minus I naught R naught minus AVD is equal to 0. So in this way, you can find out the equation for the I naught, that is V naught minus AVD upon R naught. So this is very important relationship for the current equation of the output current. So just given the equation numbers here, you would be write in this way. It will be further useful for finding out the R naught. Here R naught is the output resistance. We have to find out output with feedback. Okay, so you would be use the concept of the differential input voltage. VD is equal to V1 minus V2. That is V1 is the non-inverting terminal voltage, that is 0, grounded. 0 minus VF. So VD is equal to minus VF. We are already find out the equation of VF when we are analyzing the output resistance for voltage series feedback. So refer that particular page. You would be found that VF would be equal to, this is a voltage divided network, R1 upon R1 plus RF into V naught. Okay, so VD is equal to now minus dV naught here. So you can give it as a equation number 5 as well. Okay, so I naught, we have to substitute the value of VD from equation number 5 into equation number 4. So I naught is equal to V naught plus A B V naught upon R naught. So in this way, you can write the equation for R naught F, that is V naught upon I naught. It is equal to V naught upon V naught plus A B V naught upon R naught. Finally, you would be got the equation of output resistance with feedback, that is R naught upon A1 plus AB. Okay. So in this way, you can find that the output resistance with feedback is less than the output resistance without feedback by the factor of 1 plus AB. Okay. But in the case of input resistance, it is increased by the factor of 1 plus AB. Okay. Now the last parameter is bandwidth with feedback. As mentioned earlier, the gain bandwidth product of the single frequency of op-amp is always constant. So the gain of amplifier we have already seen in the previous analysis. It is decreases when we apply the feedback with respect to the without feedback gain. So in this way, to balance the gain bandwidth product, your bandwidth would be increased by the factor of 1 plus AB. So whatever the amount of gain would be decreased, by the same amount, your bandwidth would be increased. In this way, you can write as FF is equal to F naught into 1 plus AB. Okay. So this is your bandwidth with feedback, that is increased by the factor of 1 plus AB. Okay. So in the case of voltage feedback also the bandwidth was increased. So gain is always decreases in the negative feedback, bandwidth is always increases, you can see here. Okay. So this is all about the unit number 4. From tomorrow we would be start unit number 5. And these are the some reference books that I have referred. Screen sharing was discontinued, so there is a 4 minutes. You have not notified me that it is discontinued, so I hope this would be from the. Please take the screenshot of this output resistance with feedback. Those I do not know from where it is discontinued. Okay. So this is the reference books that I have referred to learn this, to teach you this unit. So the more important reference books are the Ramakanth Gaikwad, op-amp and linear integrated circuits, published by the PHI of Pearson Education. Second one is the Salivahanan and Kanchana Bhaskaran, linear integrated circuit by TMH. Both are reference book and very good book. You can refer either of this. But Ramakanth Gaikwad book is very nicely written. You can refer this to understand it, the concepts easily. At the same time, you can also refer to NPTEL courses. One is the web course, another is the video lecture courses are there, and both are also very good for detailed studying of this particular topic. Okay, so this is all about. Please start to fill up your attendance. So this is all about for unit number 4. Actually, I want to start unit number 5 today, but time is not left. Only 2 minutes are left here. So in the next unit, unit number 5, we would be learn the topic op-amp applications. Okay. So from tomorrow, we would be start this topic, where we would be learn lots of the topic related to the op-amp application, starting from the virtual ground and short, then inverting amplifier, non-inverting amplifier, voltage follower, integrator, differentiator, okay, and many more circuits are there, summing amplifiers. So whatever the applications we generally use, some of them we have already covered in the practical as well. We would be go into the detailed theory of this. Okay, only 32 has fill up the attendance out of 43. Please fill up it quickly. Only 1 minute is left. I would be wait for end of the time. Still students are filling the attendance. Okay, thank you for today.